Hey guys, Mr. Betts here. Let's take a look at a variety of fairly straightforward examples where we're going to have to use L'Hopital's rule. So the first one here is one that I actually did in the video where I introduced L'Hopital's rule. The only difference is I have thetas in here instead of x's. Generally, we'll use those Greek letters for angles, and so when we're doing trig stuff, we'll use theta or alpha or beta. But this is really the same problem. So the first thing we always want to do when we're doing L'Hopital's rule is first make sure that L'Hopital's rule actually works. And to do that, we want to look at the limit of the numerator of the function, and we want to look at the limit of the denominator of the function, and make sure those two limits together give us an indeterminate form, either 0 over 0 or infinity over infinity. So first thing I'm going to do is look at the limit as theta approaches 0 of sine of theta. And we can just plug 0 in for theta there, and we get 0. And look at the limit as theta approaches 0 of just theta, the denominator. And as theta approaches 0, theta approaches 0. So we do get that indeterminate form. This right here that I have written down is a necessary step in order to use L'Hopital's rule. Because remember, it only works if it's an indeterminate form. It does not work otherwise. If you remember the proof, part of the proof required that sine of theta and theta are both 0. So using L'Hopital's rule then, let me switch colors here so we don't get our work confused. We're going to look at limit as theta approaches 0. So now we're going to take the derivative of the numerator and the denominator independently. We are taking the derivative with respect to theta. So the derivative of sine of theta is cosine of theta. Derivative of theta is 1. And once we do that, we try direct substitution, and we get cosine of 0 is 1 over 1, which is just 1. So in our second example here, if we try plugging infinity in for n, we'll notice here that the numerator and the denominator this time are both going to approach infinity. So this time we're getting an indeterminate form, infinity over infinity. The notation that I have here is kind of an informal notation that shows that we know it's that indeterminate form, but we do need to be a little bit more formal about it. So we're going to look at the limit as n approaches infinity of 3n squared plus 1. Notice I put parentheses because there's multiple terms there. And that is going to be infinity. And in the denominator, we have the limit as n approaches infinity of 6n squared plus 5n. And as n gets really big, this expression is also going to go to infinity. So this work here shows that we know L'Hopital's rule is going to apply because we're going to get that indeterminate form, infinity over infinity. So we take the derivative of the top and the bottom, limit stays the same. So the derivative of the numerator is going to be 6n. The derivative of the denominator is going to be 12n plus 5. And just thinking ahead here, if we plug in infinity for n, 6n is going to be infinite, 12n is going to be infinite, so 12n plus 5 is going to be infinite. And so we still have that indeterminate form. So in this particular example, we actually have to use L'Hopital's rule a second time. So since we're using L'Hopital's rule a second time, we need to show that it applies a second time by looking at the limits of our new numerators and denominators. And both of those limits are infinite. So we can use L'Hopital, keep the limit the same, take the derivative of the top, and that's 6. Take the derivative of the bottom, that's 12. And now when we plug infinity in for n, there's no n in the expression. So the answer we get is just 6 over 12, which is 1/2. Now I do want to point out this particular limit is a type of limit that we were able to evaluate looking at relative rates of growth, or what I call dominance. So if we have a polynomial where the degrees of the terms are the same in the numerator and denominator, there are other ways that we could get to this result. In particular, since those two degrees are the same, this function as a whole is going to behave like 3n squared over 6n squared as n gets really big, and 3n squared over 6n squared is 1/2, and that gives us this result a lot more quickly, but L'Hopital's rule gives us another way to get that. This limit here is another one that L'Hopital's rule is going to apply. We can kind of in our head plug in 0, and in in the top, cosine of 0 is 1, 1 minus 1 is 0. In the bottom, we just get 0. So we have that indeterminate form 0 over 0. So to formally show that L'Hopital's rule is going to work, we're going to look at each of the limits by itself. And since the numerator and the denominator are both approaching 0, we have that indeterminate form 0 over 0. L'Hopital's rule applies, so let's apply it. So the limit as x approaches 0, the derivative of the top, derivative of cosine, is negative sine of x. The derivative of the bottom is 1. Now we try plugging 0 in, and sine of 0 is 0, so we get 0 over 1, which is just 0. Next example here, if we try using direct substitution, we're going to get, if we plug 0 in, the square root of 1 is 1, minus 1 is 0, and then on the bottom, x is just going to be 0. So we have another one here that we are going to use L'Hopital's rule, but like the other examples, we do need to show that each of those limits is equal to 0 first. So square root of x plus 1 minus 1, plugging 0 in. This is just a direct substitution limit for just the numerator. This is just plug 0 in for x. So we get that 0 over 0, so we're going to take derivatives here. So keep the limit the same. Limit as x approaches 0. In the numerator, the derivative of the square root function is 1 over 2 times the square root. We are going to have to use a chain rule here because that is a baby function or an inner function in the square root. So we multiply by the derivative of the inner function, and the derivative of x plus 1 is 1. So we're multiplying by 1. It stays the same. In the denominator, the derivative of x is 1. So this is our new limit now. And we can try direct substitution at this point. If we plug 0 in for x, we get square root of 1 in the denominator, so this is going to be 1/2. Okay, so again, that's just by putting the 0 in for x, that expression simplifies to 1/2. Another trig example here, and again, we can look at what happens as theta approaches pi over 2. Secant might be a function that we're not super familiar with, but remember secant is 1 over cosine. And if we think of this as 1 over cosine of theta, cosine of pi over 2, remember the cosine function looks like this, pi over 2 is going to be there, so cosine of pi over 2 is 0. So secant of pi over 2 is actually undefined because it's 1 divided by 0, but it's going to approach infinity, so that the secant function has an asymptote at pi over 2. Tangent function is actually really similar because it's sine over cosine. And so since theta is approaching pi over 2, cosine is approaching 0, and we get 0 in the denominator there also. So both of these functions, secant of theta and tangent of theta plus 1, they both have vertical asymptotes at pi over 2 because the limit is approaching infinity. So really what we need to do here is look at two-sided limits, and we're not going to be quite that formal. So this limit itself does not exist. Specifically, it does not exist because the limit is infinite. However, the left-sided limit as theta approaches pi over 2 from the left is going to be positive infinity, and as we approach from the right, it's going to be negative infinity. I'm not going to quite get that formal with it, but I am going to say here as theta approaches pi over 2 of secant, I'll just put plus or minus infinity. In the denominator, limit as theta approaches pi over 2 of 1 plus tangent of theta. Again, notice anytime our limit has multiple terms, we're putting it in parentheses. And same thing, on the left side, tangent's going to be approaching positive infinity. On the right side of pi over 2, tangent's approaching negative infinity. So again, we have plus or minus infinity. I'm going to be a little informal here, but I'm going to put that plus or minus there to show as we approach, I'm sorry, I did that backwards. As we approach each of these from the left side, then we're approaching positive infinity. And as we approach from the right side, we're approaching negative infinity. So I put the negatives on top to match up with the positive on top here for both of them. Okay, either way, we get an indeterminate form infinity over infinity, which means L'Hopital's rule is going to apply. So, limit as theta approaches pi over 2. Derivative of secant is secant of theta times tangent of theta. Derivative of tangent is secant squared of theta. Lots of trig stuff here. I think it's obvious that the secants are going to cancel each other out. It's not as obvious, but we're going to have a little bit more canceling. Ooh. Sorry, let me change that back. So we are going to have a little bit more canceling with the tangent and the secant that remains. Remember, tangent is sine of theta over cosine of theta. So I'm replacing tangent with that. Secant is 1 over cosine of theta. So these cosine of thetas in the denominator are canceling. And so really what we have here is the limit as theta approaches pi over 2 of the sine of theta. And as theta approaches pi over 2, sine of theta is going to approach 1. Now, I do want to point out here that this informal limit notation that I did earlier, really, to be completely rigorous about it, I should have split this up into 2 one-sided limits. It does turn out that in this case, each of those one-sided limits is going to approach 1. And I will also say that you rarely see problems where that's going to be the case. So I'm not going to really emphasize that here.